All right, so good news, everybody, is I've done the first question with everybody. So we're completing the rest of the chain rule notes that I am doing as a goal. So again, what my main goal is to kind of color code through this, make sure we can understand. So again, as we do these problems, I want you to think about that Matryoshka doll idea that I was giving you, the idea that we're going to deal with an outer function to an inner function to help this out. So going through these problems, we're looking for an outer function, 2/3, an inner function, x to the 4th plus 2. And just like we've been saying, we have to deal with the derivative of the outside piece first. So I look at the outside piece. I'm going to take this 2/3. I'm going to do the power rule on that. So 2/3 times whatever I was multiplying to the negative 1/3. We will get x to the 4th plus 2 here, because that's not going to change. The derivative of the power rule, we have to do one derivative rule at a time. And then we're going to multiply this by 4x to the 3rd. And if we go to simplify this, we find out that dy dx, the 4 times 2/3 is 8/3. And we get the 4x cubed the x cubed is going to have a positive, so that's going to be x cubed. And the x to the 4th plus 2 to the negative 1/3 is negative. That will move down to the denominator. And we're left with our final answer. Just as a chance to review this, if I stop here, this would be considered a safe stop for your FRQs. This is what I expect in multiple choice. You have to be able to play the game and do what they ask you to do. And when we get to the next set of notes, we're going to see an example of that, making it really clear why we have to pay so much attention. All right, the next question. Looks a lot like a quotient rule. I've got a division. I've got this down here. But what I want to point out is there's no x variable inside this problem, inside the numerator. And we're only going to quotient rule if there's going to be an x, a variable in the numerator and the denominator. So I'm going to take my opportunity here to make my life easier. Now what I want to point out is it is not incorrect. It is not incorrect to do a quotient rule here. You can do that, it'll work. But it's extra work. And part of calculus is doing the most efficient thing at the right time. So we're not going to use the quotient rule. We're going to go ahead and set this up with a negative exponent and utilize that to make a simple chain rule problem. Again, we look, the outer function is the negative 2nd power. So when we take that derivative, we would multiply the negative 2 times the negative 7 to get 14 times something to the negative 3rd power. And that something is going to be the 2x minus 3. And what I told my 3rd period that I didn't really mention to the other classes, you'll notice I've been writing the 14 parenthesis, close the parenthesis, did that, and then I would write this in the middle. That's not necessarily how you have to do that. You may write 14 parenthesis, copy the 2x minus 3, close that parenthesis, negative 3. That's fine. I'm doing this because I'm changing colors, and it's easier to do it this way. Continuing where I'm at, this is 2x, so I'm going to multiply that by 2. That's my derivative of 2x minus 3. And then we simplify to get 2 times 14 is 28. And then 2x minus 3 to the negative 3rd would go into the denominator. 2x minus 3 to the 3rd power. There's your final answer. All of these are very similar. They do the same type of process. This next one, looking at the same concept. This one does have a small thing to throw a monkey wrench in the problem, and we'll see that in a second. The 5th power is the outer piece. So we take the derivative there. 5 times 2 is 10, times something to the 4th power. Again, that something is now 6 minus x squared. The derivative of 6 minus x squared is not 2x. Most common mistake, people go 2x, they get it wrong. If you notice, there's a negative here. The actual answer is negative 2x. So realize that that minus sign is a sign that's attached with the x squared. Negative 2 times 10 is negative 20. I've got an x, so I'll leave that out here, times 6 minus x squared to the 4th power. Ladies and gentlemen, I give you the chain rule. Now, the other thing about the chain rule is that this also works with trig functions. Just like any other problem, trig functions is going to be an outer function, in this case cosine, and an inner function, 3x. So we're still dealing with outers and inners. It's just not going to be an exponent rule. You'll notice now this is actually what you'll see in a calculus textbook, and this is what I was talking about earlier, how the definition of the derivatives are actually going to have a chain rule. Du dx is just whatever that u is. Remember that u could be a 3x, it could be a 4x, 5x, 25x, 36x. Could be another trig function, cosine x, tangent x, whatever. That u, if we take the derivative of u with respect to what the x is, we're going to see what our answer is going to be. So now this works for any sine function, any cosine, any tangent, any secant. Now we've got something that works for all of them. So again, what we'd expect, we take the derivative of the outer piece. Derivative of cosine is, of course, the negative sine of something. That something happens to be a 3x. We multiply by 3. We get a final answer of negative 3 sine 3x. We can do that for any of these problems. Here, the outer function is sine. The inner function is 5x squared. So when we take this into account, we say the derivative of sine is cosine of something. In this problem, our something happens to be 5x squared. So what do we get? We have to multiply by the derivative of 5x squared to get 10x. What's my final solution? My final solution is 10x cosine 5x squared. And it even works with something as difficult as a cosecant, even though we're not a fan of cosecant. Remember, cosecant is a really goofy looking argument here. But when I take a look, we've got cosecant as the outer function, 7x to the 5th is the inner function. So, derivative of cosecant is the negative cosecant of something times the cotangent of something. Those somethings happen to be 7x to the 5th, 7x to the 5th, which means we need to multiply by the derivative of that 7x to the 5th to get 35x to the 4th. A little more complicated response, but 35 times the negative is negative 35x to the 4th, cosecant of 7x to the 5th, cotangent 7x to the 5th, and we call that a day. Those are probably the most common trig values that you're going to deal with, but there will also be weird situations where I'll have a trig function embedded inside of another trig function. You're using the same exact rules, folks. You identify the outer function, you identify the inner. You take the outer layer of the matryoshka dolls, you're going to take off that head, which means kind of like doing the derivative. So if I do the derivative of tangent, that is secant squared of something. What is that something here? Happens to be the sine of x times the derivative of the sine of x, which is the cosine of x. So when I put this all together, now this is an interesting one, and I'll talk about this in just a second. Sine x cosine. I'm going to put the time so I know that that's separate from the secant. Now, things I want to point out. There will be some students in here, and if you are okay with this, if you don't want to get confused by this, that's fine. You can kind of skip over for the next couple minutes. It'll probably take about a minute for me to describe. But there will be some students who will recognize secant as 1 over cosine. And what they're going to say is that this is really the 1 over the cosine squared of the sine of x times the cosine of x, and they're going to want to cross off the cosine from the squared and leave this as just secant of the sine of x. This is a completely wrong thought process. and I want to make sure to address it now. Things we're looking for with trig functions, and I know that most of you know this stuff already, but I just want to make sure that we're good with this. So what do we have? Well, first, to make sure that these things cancel out, you have to have the same exact argument. This has an argument of cosine x. This has an argument of x. So that cosine squared and that cosine have nothing to do with each other. They're not having the same inputs in either of those functions. And that's the biggest issue. Other students will want to say, well, other students will take this and they will make the following mistake as well. So one is the arguments. The other ones is some people want to call this sine of x over cosine squared x. And they want to call this sine over cosine is tangent, so they want to call this tangent x secant x. Again, this is going to be another problem. The biggest thing I want to ask is, where on earth did you get the x for the cosine? I don't see another x in this problem. This is the secant of the sine. Be careful of how you simplify your trig functions. Don't make a silly mistake on that. Hey, that took about a minute, minute and a half. Okay, cool. Last set of problems I then want to address then, going back, a couple of old questions, a couple of these are old. I'm actually going to do this one first. So looking at this, I look at the relationship. I see that this is a quotient rule. In fact, tell you what I'm going to do is on this problem and on this one where we have a product rule, I'm just going to give you the answers. And if you want to figure out how to get to the answer, I'm going to allow you to figure out how to do that. We've done examples like these before, so they should not be surprising. The answer to this quotient rule is negative 9/8. And the answer to the product rule is going to be negative, this is h prime of 3 is negative 9/8. This is h prime of 3 is going to equal negative 38. Let me double check that. Yes, negative 38. Those should be things that you can do on your own. Ho-de hi minus hi-de ho all over ho squared, or first times the derivative of the second plus second times the derivative of the third, plug in a value. I want to make sure that we get a chance to see how this works with the product rule, though. So if I want to find h prime of 3, this right here is a chain rule. So again, I'm going to do the outer function and the inner function. So if I want to find h prime of just x, notice not 3 yet, I've got to do x before I find 3. The derivative of f is f prime of something. In this problem, that something is the g of x. That doesn't change. Take the derivative of the outer piece, do nothing else to anything else. And then I'm going to take the multiply this by the derivative of the inner piece, g prime of x. So if I'm looking for h prime of 3, I really have the f prime of the g of 3 times the g prime of 3. Well, let's simplify this. G of 3 is over here, 4. So now this becomes f prime of 4. G of 3 has a value. It comes out here, and I'm going to leave this as g prime of 3. So f prime of 4 over here is 8 times the g prime of 3, negative 5. You get a final answer of negative. Fine, don't write it all on the board. There it goes, 40. So that's what we're looking at. That's a really quick crash on several example problems. Hopefully those make sense. If you get a chance, try these out. For those of you who are looking for added difficulty or maybe something a little more involved, the last 3 problems are interesting. In the way back when we did this one, way back, like I did it just a million years ago, but I just did it 14 minutes ago. In problem C, I said that that was not a quotient rule because we did not have an x in the numerator. You'll notice now, in a question like L, you'll see that there's an x in the numerator and in the denominator. We can have to deal with product and quotient rule. Product rule up here, you'll see that, hey, look, there's a product here. So there is a first and there is a second, but in that second we can see that there's an outer and an inner function. So when we take the derivative of the second piece, there's going to be a chain rule built in. That's what we're going to talk about tomorrow. That's what we're going to be looking at. Same thing here. You'll see there's a quotient, but inside your low, you have a chain built in. And in your final problem, you'll see that this is a chain rule now, but within the chain rule, when I take the derivative of the inner piece, you can see that there is now a quotient. So that's the type of thing we're going to deal with. That's what we're going to start tomorrow off with, looking at these three situations before we do practice problems. Thank you for your time, folks. I appreciate you making sure to watch this. I look forward to seeing you all practice the chain rule tomorrow. So get some good sleep. Make sure that you're kicking butt. And don't forget to wear your Western wear. Awesome.